Good afternoon and welcome to today's webinar on the tsunami debris modeling. My name is Althea Rizzo. I work for the Oregon Office of Emergency Management as the Geologic Hazards Program Coordinator. And this is one of the webinars that we have put on around the topic of tsunami debris and response and recovery after a Cascadia style event. We are planning on putting on more of these webinars over the next year or so. So be sure to check your emails when you see these invitations on your inbox moving forward. These webinars are an outcome of a seminar that we held last year in Astoria, Oregon, between the states of California, Washington, Oregon, and the Canadian territory of British Columbia. We are working on some other products out of that seminar, and we look forward to sharing those with you when we are complete. I have everyone muted right now. We will have time at the end of the session for questions. If you want to make sure that your question can get asked, feel free to put it into chat, and we will address your questions there first, and then we will go to open mic afterwards. So I would like to turn the floor over to Dan Cox of Oregon State University, and take it away, Dan.
Thank you, Althea, and thank you everyone for joining the webinar today. It's my pleasure to be able to talk about some of the work we're doing. I'm a professor here at Oregon State University in the School of Civil and Construction Engineering, and very fortunate to be able to work with people, graduate students and other researchers. Young-Soo, Kameshwar, Shafiq, Dylan, and Andre have all contributed to this work. And it was sponsored by the NIST Center for Risk-Based Community Resilience Planning. And it's basically trying to look at these large disasters and what we would need to think about in terms of trying to reduce damage and then speed up the recovery effort. And the tsunami debris piece is really interesting. I think on one hand, just looking at the picture in the background from Kesennuma in Japan, there's just a whole lot of stuff there that wasn't there originally. You know, unlike just an earthquake where the debris is generated, the tsunami is also going to move it around a lot. And that's one of the interests that I have right now, is trying to figure out how well can we predict where that debris is going. Rick Wilson gave the last webinar, and for those of you who were there probably remember, it was really interesting to he showed a lot of the work that's going on in California and some other places, including work by colleague Pat Lynette, showing the probability of debris moving from one location to another. So this is somewhat similar in that vein, is trying to figure out how much debris is generated and where does it go. So the next slide, this is closer to home. It's a hurricane debris field down in Texas after Hurricane Ike, and you can see one of the impacts is that the debris starts to just cover the transportation network. And so if we can't think about where that debris is going to end up, it's going to impact how quickly we can respond, number one, and then also recover after some time. And trying to understand what kind of debris also lends itself to what kind of equipment is needed. You can see the boat in the foreground is going to need a different type of removal equipment than some of the smaller debris around it. Rick also pointed out a really good document. This is, I wanted to mention it again, this is FEMA P325. It's a public assistance document for debris management, and it's really good. It's chock full of a lot of useful information, and it's what we used here to inform some of this study. So again, highly recommend that document. It's kind of arranged with starting with debris forecast, which is the topic that I wanted to talk about today. And then it goes on to a lot of other important issues, like how you collect the debris, how you manage the debris sites, how you do reduction and recycling, and then finally the disposal. So there's lots of interesting components to this debris issue, and today I'm just going to talk about the first part, which is the debris forecasting. The FEMA document also does a really nice job to categorize different hazards. So in this table on the column on the left, it's looking at different natural hazards from hurricanes, tsunami, flood, tornadoes, earthquake, wildfire, and ice storm. And then going across, it's the different types of debris that we have to consider, grouping it into two big classifications. One's natural debris like vegetation, mud, that kind of stuff, because the disposal of natural vegetation can be a lot different than the man-made, natural debris can be a lot different than the man-made debris in the next columns. Things like, the picture on the first slide shows a lot of construction demolition debris. So those are broken up wood frame houses, for example. Household and hazardous waste, that's also treated separately because, it has to be disposed of differently. White goods are things that are, oftentimes made out of steel and can be separated with electromagnets. And, these are washer, dryer, that kind of stuff. And then vehicles and vessels, hazardous waste. So these are all different types of debris that have to be considered in a debris plan. Today, I'm just going to talk about what's circled there is the construction demolition debris. So these would be components of buildings and only from the tsunami. This is our, the really, really big one. This is the Cascadia Subduction Zone on the left, going from Northern California up to Vancouver Island, British Columbia. And then on the right-hand side is the city of Seaside, which we've been using for about 10 years now as kind of a specific site where we can think about some of these concepts and again, very interesting for us and important because of the exposure to the Cascadia Subduction Zone. In addition to the buildings that you saw in the last picture, we're also focusing on what we call critical facilities and lifelines. So this would be, for example, the transportation network, including the bridges, power networks, water networks, communications, cell phone towers, and then also things that are needed in the immediate aftermath of a disaster. So hospitals, fire departments, police departments, schools for evacuation areas and things like that. We did a lot of our own tsunami inundation work. I think initially we wanted to get kind of a better handle on what the inundation looks like, and then we wanted to build up what we call a probability map. What's the likelihood of getting certain levels of tsunami? So I won't dwell too much on it, but a lot of the inundation dynamics are stuff that we did ourselves here. And again, what we're trying to do is to put a recurrence interval associated with certain levels of flooding. So for example, the middle graph shows the flooding extent for the city of Seaside with an annual exceedance probability that would correspond to like a 1,000-year event. So the previous earthquake and tsunami from the 1700 event, that would be roughly equivalent of around a 500-year event or something like that. And then with earthquake design for structures, usually we're considering something up to a 2,500-year event. And what this allows us to do, for example, is everywhere in an area, for example, like the city of Seaside, if we wanted to know, for example, what's the flood depth associated with this 1,000-year event, we can do that. So the figure on the right would show where this yellow star is, for example, a 9-meter flood depth would have a 1,000-year recurrence interval or probability. We also do the same thing for the velocity. So we know a lot of details about the tsunami as it flows in, and we're going to use this velocity later to help us move the debris around in the town. And a third type of map that we create is called the momentum flux, and this is just basically how strong the water is, or the force that would be associated with the water. That's a product of how fast the water is moving and how deep it is. So engineers typically use this quantity to help calculate the likelihood of failure of a building, and I'll show how that gets used a little bit later as well. This is a little bit new, and one of the things we're working on is a duration time of flooding. So for example, if first responder wants to go back into an area, they may want to know how long will the water be above a certain threshold. So for example, if they have criteria for vehicles and things like that, they want to know what the flooding level might be, how long will it take to drain essentially. So we're also working on some of that. We don't use it directly in the debris part, but I think eventually we have to think a little bit about what's the duration at which the, how long is the water going to be there? How soon can we get in? Just to reorient people a little bit with the aerial view of Seaside, in the center you kind of see the central business district. There's the, I think formerly called the Trend West Hotel, so a large hotel in the waterfront, or condominiums, and then hotels. And for people not familiar with the area, it's mostly residential wood frame on either side. So it's mostly wood frame construction. And then as you get further from the shoreline, it's kind of a mix of residential and commercial. And what we wanted to do initially was, for every single tax lot, we wanted to know what's on that tax lot from an engineering perspective. Like, what's the building made of? How high is it? Is it likely to withstand a certain level of earthquake, and so on? And we used 3 different tools to build up our inventory of the built environment there. One was a tax database, which gave us a lot of good information about the year of construction of buildings, for example, how tall the building was, what it was typically used for. We also did Google Street View, when we also made several reconnaissance trips up there, and just did use a rapid visual screening tool from FEMA, especially for a lot of the important buildings that we talked about earlier, so we could kind of characterize those buildings. So our built-up inventory of the built environment is looking at the material type. Is the building made of wood or concrete? How tall is it? Is it 1 story or up to 5 or more stories? And then the third panel is the seismic code. So just based on the date of construction, we have rough estimates. Was it built pre-code? So there was no standard enforced for the construction related to seismic. Or is it a more recent building? These are the ones shown in red, which are built to high seismic code or current seismic code. So again, trying to classify about 6,000 buildings to describe the built environment before the earthquake and tsunami. So an example of how we do our damage assessment is, again, let's say, for example, the hotel on the right, we want to know for a given event, let's say this 1,000-year event, what's the likelihood of having a certain level of damage to that building. And from our inundation study, we would know that the level of flooding there would be about 4 meters. We know that this particular building is made of reinforced concrete, it's 5 stories, and was built to a moderate seismic code. With that information, we can predict that there's about a 10% probability, which is fairly low in this case, that the building would collapse. So it's actually fairly low likelihood of collapse for that building. And so we just paint it yellow, you'll see in the next picture, or paint it green, I'm sorry. Right next to it, just slightly out of the frame, was a 2-story wooden building, and that would have a different probability curve associated with it. So same level of flooding, but in this case, there would be about a 90% chance that that building would be damaged as a result of the earthquake and tsunami. So these fragility curves all come from the HAZUS manual, or HAZUS document. So this is a federal document from FEMA that in Oregon and other places we can use for estimating the likelihood of damage. So in our case, we use these fragility curves, and we can very quickly look up for all of the buildings what would be the likelihood of damage throughout the city. And this is a map with a little bit of detail with the central economic zone here shown in a much lighter color, green and light green, indicating these have a much lower probability of collapse, and then the wood frame buildings are much more susceptible to the tsunami, and so they would be 60 to 100% probability. We can repeat the same exercise with earthquakes, so that's shown on the left, and we see a little bit of an opposite trend where the concrete buildings are more heavily affected and the wood buildings are less affected. The tsunami that we just talked about, and then we can combine the two to look at what's the likelihood of and the extent of the damages that we would see from each event, going from 100-year, 500-year, 1,000-year, and so on. So here's a picture that shows, for example, up at the top, if we looked at the 100-year event, things look green, which is good. There's a very low consequence. There wouldn't be much damage for the event of 100-year. And then as you go all the way up to, for example, the 2,500-year, 2,500, then you start to see these would be much more higher consequence. And then somewhere in the middle is what we term the highest risk case. So where would the combination of likelihood of the event versus the consequence of the event. When you combine those two numbers, you start to figure out where's the highest risk. And I'll show this again on this slide. If we look at the red line here, it's showing for the 100-year event, okay, it's more likely to happen, but lower consequence. And then at the other extreme, we have higher consequence, but not so likely to happen. And then it's really in the middle where we start to look at 500,000-year events where we've got the biggest risk that we have to worry about. This is for looking at tsunamis, and then we can also look at earthquakes and then combinations of earthquakes and tsunamis. So we're spending a lot of time to try to understand risk for the buildings, and then also for water, electric power, and roads, doing the same kind of risk analysis. And then based on this damage, I know this isn't very exciting to throw up the equations, but just to show there's some real numbers behind here where we try to look at what's the expected damage fraction of each of these buildings. So again, going back to each building and trying to estimate for the given amount of damage that we're predicting, how much debris do we think is going to be generated? So a lot of this, again, is based on HAZUS, comes from observations of earthquakes and then trying to go in and clean up after earthquakes. So we're working primarily with earthquake and trying to extend that to tsunami. So our results look like this. There's a clip of the city of Seaside, just the central part down below, so you can kind of make sense of this distance chart at the bottom. But zero is at the water line, so at the beach area, and then going into land. So 2,500, that's more than a mile. 1,600, that would be about a mile here, so almost a mile and a half going inland. And the y-axis is showing how much debris would be generated as a result of these different types of events. And the blue line would be a 250-year event, and then going all the way up to a 10,000-year event. You can see that most of the debris would be generated near the water line. So this is trying to, hopefully you guys can see the cursor moving a little bit. And then this dip here corresponds to the Mechanicsum River, which is about 500 meters inland. And then it picks up again right around Highway 101, and then it dies off. So our question is, what happens to all of this debris that could be generated? Is it going to stay here, or like in the pictures that we started with, with the boats and the roads, is it going to get washed inland? So our next job is to say, okay, I figured out how much debris I create. Let's estimate what portion of that would be buoyant. And so, for example, looking at the picture on the right, you can see that the houses to the north and south, they're made of wood, so there's going to be a lot more buoyant material that's being produced to the north and south. And then the central core, although there is some debris generated, it's made of concrete and brick, so it's less buoyant and it's less likely to move in. So we can estimate based on the type of construction how much of this is going to be made of wood. And now let's try to push it inland. And this is, again, very similar to what Rick Wilson was showing at the previous webinar from PatLineNet, where you can use these particle tracking models, and they basically can push the debris to where we think it would go based on thresholds of the water speed and thresholds of depth, which would be the same thing as a ship running aground, for example. So if, in this case, these blue dots, if the water depth goes below 1 meter, 3 feet, then that dot is going to stop. And then the last one, hopefully these videos are coming across over the web, but the last one is for really small pieces of debris. So for example, 2x4s and things like that, then it would just wash almost what commonly called the rack line. So this would be the line of maximum inundation, close to the 379 line, for example. So those are the ways that we push the water. The water, for example, pushes the debris inland. Let me see if I can advance the slides. And the result is, kind of a before and after. So before, this is a total map of the debris field generated from the event. And then the right-hand side would be much more likely picture of what that debris field would look like for the city. And again, this red line going north-south, this is the extent of the maximum inundation of the tsunami for that event, very close to the 379 line. And then these orange and red blobs, those are hotspots of the debris where we think the debris field would accumulate based on the computer simulation. So it's not uniform, but there is a general trend that the debris kind of settles, if you will, up on this rack line, so at the furthest extent of the inundation. There's stuff on the other side of the inundation line, but that's from the earthquake. So these would be, for example, things that were debris that was generated to buildings outside the inundation zone from the earthquake. But the red hotspots are all from the tsunami. So again, going back to this chart we showed with how much debris volume is generated, this would be the before, and then this is the after. And so this is showing how much change you get as a result of the tsunami. And it's really different than what, for example, HAZUS would predict. HAZUS can just tell us amounts locally, but I think we've got to think a little bit about how it would get pushed around in a, along our coast, going up and down Highway 101. I'm going to flip back and forth one more time. So this is the pre-condition, or the simple result that we would get from a model like HAZUS. And then if we can push the debris, this is what it will look like. And these really large events, like for example, the black dotted line is the 2,500-year recurrence interval. That would be close to the large or extra large event, if you're familiar with the Dogami nomenclature. So this would be really large event, and this black arrow at the top kind of shows the mean inundation line, and then you can see that the accumulated debris is really close to that inundation line. So first result I would take away from this type of work is that, in addition to looking at the tsunami inundation as a zone, I think we also have to think a little bit carefully about the line itself and what potential there would be for debris accumulating close to that inundation line, especially for things like transportation routes and things that are needed to either immediate response or recovery after a few days. So here I'm just showing another chart, a very similar type of thing, but kind of before and after. The black line is the before, and the red dotted line is the after. And then the first three panels are different locations in Seaside going north to south. And if we look at CC prime, for example, this panel, this is where we're showing, again, these kind of hot spots where you get these really big red blips. That's like those hot spots that we were looking at on the map. And again, it's just showing you between black to red. Okay, initially I had no debris. Now I've just got, you know, a huge volume of debris. And then if you look on the chart here on the right, that kind of corresponds to where we've got two important facilities. One is the hospital and one is an assembly area or a school. And so trying to map out where do we think we're going to have large debris fields, and then do we have anything that, you know, we really have to think about that, you know, if we're going to be used in the immediate, you know, immediately after the event, then we would have to think about, you know, okay, maybe there's a way we have to prioritize the debris clearance to access these facilities. So again, I'm just kind of highlighting it a little bit more. This is still kind of work in progress, not super polished, but highlighting, for example, the hospital in Seaside. In this case, there's really one main access point getting into the hospital. And in this case, if there's a large debris field that would settle there, then that would have to go into a consideration on, you know, kind of clearing that debris or getting rid of that debris, and knowing how, you know, what type and size of that debris. So hopefully, that, you know, our hope is that at some point this type of work can be useful for the planning of debris removal, which would be that next step in the FEMA chain. And then, for example, within the inundation zone, although, you know, there could be other complications, at least you could say that the fire station would have multiple access points, and at least from a debris perspective, you wouldn't find the same hotspots surrounding the fire station. So I'm just trying to look at different types of facilities in that inundation zone as well. So this is kind of raced through it. Alfia kind of ended a little bit sooner than I thought, but we're kind of, I feel like we're kind of scratching the surface a little bit on this one, because we only looked at buildings. You know, there's only one type of debris. You know, obviously large vessels, boats, vehicles. There's other parts of our coast that are more, you know, have a lot more vegetation. Even sand, even though it doesn't float, still a lot of sand is moving around. Like in Sandy, Hurricane Sandy, we ended up moving. You know, there was a lot of sand that had to get pulled off of the roads before people could go in for recovery. So looking at other debris sources, and you know, whether it's buoyant or not buoyant, this was only a buoyant exercise, but a lot of work that I think we could potentially do there to get a better picture. And then the third bullet item, you know, recognizing not every location can have a super high level of detail associated with it. So at some point we have to come up with general rules like, is it the local topography or local land use that would then create these types of hotspots? So we're trying to come up with, is there a way to generalize these trends so that we could maybe, at least as a screening tool, use it, let's say for along Highway 101 or along the inundation line, how we could potentially screen for hotspots that then would warrant a more detailed analysis of the likelihood for debris. And then the last bullet item is debris clearance and removal, and something that, you know, how the forecasting work would feed into that next step of clearing the debris, at least initially for recovery or response, and then debris removal for longer recovery phase. So that's kind of where some of what our work is. Just a diagram kind of summarizing what we're doing, very busy diagram, but happy to take questions, a little bit of discussion, and my email is up here if anybody's got any wants to follow up with any discussions. We wrote a few journal papers, and I'll be happy to send those out if people want to read any more detail. Thank you.
Thank you, Dan. Thank you, Dan. We do have a couple of questions in the chat. So if you do have questions, please put them into the chat so that I can follow up on them. First question is, are these debris models or similar models available for use by community planners? If not, how difficult would it be for a platform to be created and made available for planners to use in these models in the future?
Yeah, that's a great question. I would say initially for planners, the HAZUS tool, I think one of its biggest uses right now is for debris estimation. So I think just to estimate volumes of debris, probably the HAZUS tool is better. And then I think if it's looking at how the tsunami moves the debris around, I don't think there's anything off the shelf right now that would do it. I think it would have to be kind of a discussion with, yeah, we just have to dig into that one. But I don't think there's an off-the-shelf tool that a community could use to figure out where the tsunami would push the debris. I think that's really the last point I was trying. One of the last points I was trying to make on how we can generalize these results. So if they had a HAZUS result and then they want to figure out where does it get pushed to, we've got to work to generalize it. I know that was a little bit of a non-answer, but so yeah, I would say these tools aren't readily available for a community other than the HAZUS forecasting tool that gives you a total volume.
Thank you. What model did you use for debris transportation advection model? Could you please tell a little bit more about it? Slide 30. Thank you.
Yeah, sure. So the debris advection part came from the work that we were doing here at Oregon State University. And again, we started with wanting to map the tsunami ourselves, just so we would have a better sense of what we were doing and being able to predict these different levels. So the modeling was done here, but we didn't use our own models. We used, see if I can find the picture here. So we used NOAA's model for the source. So this was to simulate the Cascadia Subduction Zone. We used the NOAA model. And then for the finest grid, we used the model from Pat Lynette at Southern California, which is called Cool Wave. And that allowed us to do the detailed simulations in Seaside. And then for the advection, we added some very simple rules about when does a particle start moving. So these are kind of rules that we typically use for sediment transport, for example. There's a threshold, and above that threshold, the water will move the debris. And then we also needed to get the debris to stop, because otherwise it would just wash around forever. And so we implemented a simple rule on grounding that if they were in a cell that had a water depth that was below a certain threshold, then that debris would stop unless more water came along to push it. So very simple rules on the threshold for initiation and stopping the motion. And we just kind of added that ourselves here.
Thank you. So the next question is, what friction factor are you using in your modeling?
Good question. This one I'd have to phone a friend. It would be Hyung-Soo Park, who's now a professor at the University of Hawaii. He did the modeling, and I would be guessing on the friction factor, to be honest. I know he did a nice study looking at different values of the friction factor and how that would change the velocity, but I can't remember the one that he used for this one. I'm sorry.
Thank you. And if you follow up and find that out, I can send it out to the group.
That sounds good. Yeah, sounds good. And by the way, I think for the group, if I'm presenting a lot of work that Hyung-Soo is doing, I'll be happy to share his contact information, although you can probably find it faster just typing Hyung-Soo Park at University of Hawaii. And I'm sure he's pretty excited about this work and would be happy to talk with people too.
Excellent, thank you. I smell a possible future webinar. Okay, so does the model assign mass to the debris? Also, does the model include debris interacting with other debris or structures?
That's a great question, and probably should be one of the bullet things at the bottom. The answer is no to both. There's no mass associated with it, so the particle, once it's moving, just follows the water wherever the water is going, and until it hits that grounding rule. And then the other one is that there's no interaction between the debris themselves. Like, they don't slow the water down, they don't slow each other down. There's no interaction at all. If you there's some nice modeling, for example, that again, going back to Rick's presentation 2 months ago, where you could see some of the ships moving around, and those ships they can bump into each other and bump into the pier and that kind of stuff. Those models work really well when you have up to maybe a dozen or 2 dozen particles. But if you want to do like what's in this picture here, thousands of, just tens of thousands of pieces of debris, it would be pretty challenging at this point. The boat in the middle, though, I think you would want to have maybe more of a model like what Rick was showing last time, where you're really tracking more of the physics, because there's just one boat. There's thousands of pieces of 2x4, but just one boat, so you could afford to do that one more carefully.
Thank you. Next question is, can you comment further on the quality of the model used to advect the debris to other areas? And has this been validated against real-world examples such as Japan?
Yeah, that's a great question. So the short answer is no, it hasn't been validated. Other than it looks better than not advecting at all. Like if you just use, let's say, for example, a FEMA result and it creates debris, well, we know the debris is going to go somewhere, and at least we were able to push it to the rack line. So I'd say qualitatively, it seems to do what it's supposed to do. Hyung-Soo right now did a bunch of lab studies where he's trying to test out some of these simple rules, and so he's trying to validate it against some laboratory data. In the future, it would be really important to be able to validate it against the type of debris from Japan or other disasters. One of the issues is, although the debris is counted, like they spend a lot of time, because they pay per ton or per volume or per truckload of debris. There's a lot of careful numbering there, but once it's been collected to sometimes an intermediate site, so it's not necessarily, they don't have that accurate information of the debris where it ended up as a result of the tsunami. They have a lot of accurate information of the amount of debris that's in a pile somewhere, and so that's a little bit, at least we could maybe validate volumes, but it's still pretty hard to validate the exact locations. But I appreciate the comment that trying to validate the debris is a really important next step.
Thank you. The next question is, do we know if there will be subsequent tsunamis after the initial tsunami?
If we wait long enough, there will be another one. No, I don't know. I think there are, well, definitely within the same event, there can be multiple waves. Our inundation, and I believe the work from Dogami as well, shows, at least in this area, the first wave is the largest, but that's not necessarily true everywhere. So you could have multiple waves of that one event, but how fast the next, I'm not 100% sure if the question is like in terms of minutes to hours. That's certainly possible and oftentimes likely, but not days apart. That makes sense. Yeah.
So the next question is, does the distant inland take into account elevation?
The short answer is yes, and that I think that elevation is really a key question, because our first look is that the areas where we have the hot spots, I'll see if I can bring up the picture real quick. Yeah, so these hot spots seem to correspond to areas of low elevation where the water seems to swirl around a little, if you will. Also related to how much debris was upstream, so to speak. But yeah, it's a great question about the elevation. It's accounted for in the model, and I think there's something with the lowering of the elevation locally that kind of promotes this hotspot. So it's something that we want to look at in the future.
Thank you. Next question is, since currents are strongly dependent on friction, how confident are you in the volumes of material moved? Is there an uncertainty factor that could be incorporated?
Yes, that's a great question. The friction itself definitely, can affect the velocity, and then, all this is based on the velocity. So definitely trying to think a little bit about, if we vary the friction factor or vary it spatially, how would that change the results? That's a really good question. I think another one could also be, so for example, we don't include the built environment itself. So for example, if there are buildings that didn't, that survived, our model doesn't account for that, and the debris would, in a sense, sort of like just sweep right through it without it being there. So we don't really model the actual buildings themselves, the water flowing around the building. So I think there's a lot of, you could say, uncertainty with that. So yeah, I think those are probably the two biggest ones on the velocity. I think there's probably an equal, if not larger, uncertainty on the volume of debris that's just being generated from these fragility curves. So I know a lot of it was based on earthquake, but I don't know how much of it has really been validated from FEMA on the tsunami. So probably we've got two big sources on that one.
Thank you. I think you answered the next question with this last answer, but does the modeling take into account flows around the buildings left standing?
Yeah, that's a great question. The answer is no. And there are a few models I've seen, just going to research meetings where they can do it, but most of the, the models, the results for hazards planning don't include that yet. And that's the ASDE work, Dogami, other places. There's just not enough computational time to do it. But I think at least if we could do it once and come up with some general rules, I think that would be better than nothing. But yeah, at this point, we don't account for it.
Okay, thank you. So last chance to type in your questions into the chat. And while you do that, I'm going to go back and revisit the question about whether there will be subsequent tsunamis after the initial tsunamis. And the answer to that is possibly. If we have an aftershock that is large enough to generate a separate tsunami, then yes, we could have subsequent tsunamis. We've seen this in Japan. We saw that in Indonesia in 2004. So if we do have large enough aftershocks, those can also cause another tsunami. Good. So we have another question coming in. Washington DNR and the U of W is doing modeling for tsunami inundation in Puget Sound. They are also looking at finer scale modeling for planning a maritime mitigation strategy with Washington Emergency Management. Could the models be calibrated to provide a more robust planning tool?
Yeah, I'm not really familiar with what they're doing, but I think thinking a little bit about what Rick presented last time, I think if they're working on maritime and for example, ships, boats, I think considering the debris would be important, would love to talk with them and maybe they could give a webinar too. It would be kind of good to see what they're doing. But yeah, I think there are ways to try to bring debris, either kind of a simple approach like what I'm doing, or maybe a more in-depth approach if there's a few important pieces of debris similar to what Rick showed last time.
Excellent, thank you. So this is your last chance to type in a question. I'll give you a few seconds to at least get started so we can see that you're in action.
And while people might be thinking of their questions, I think I'll add maybe one more to the questions about uncertainties. I think these are really good questions, because if we're not somewhat confident in what we're doing, if we don't validate it or do anything like that, it's hard to use it for any type of real planning. I think for me the result of the exploratory research, you could say, is it's different. It's different enough from not doing it that it's worth, okay, let's pursue it. Let's try to get a little bit better number. Let's do lab experiments or field work or something like that. So I guess that's kind of where we are in the stage, rather than kind of rolling it out and saying, and going to the city of Seaside and saying, here's what your debris field's going to look like. I think as a researcher, I'm really just saying, hey, we've got, the maps from the left to the right, they're looking different. So now we have to start thinking a little bit differently about, how does this impact the next step, like the debris forecasting? How does that lead into I'll jump up to the last picture, the picture here, the debris collection, debris management. And from that side, it's like, well, how accurate of a number do you need in order to improve the debris collection and debris management? So part of why I also want to be a part of this group is to try to understand the rest of the cycle. We'll never perfect the debris forecast, but as long as or do it perfectly, but at least if I can improve it, or we can improve it to better do the collection and management, then I think we're moving in the right direction. So that's kind of where I'm hoping the research leads to, and would love to talk with people who are doing these other steps too, and kind of see, well, how does our work relate to what people need to do in terms of the debris management.
So Carrie Garrison-Laney has typed into the chat that she can speak to that question. They're working on the Maritime project in Washington. We have the capability to show particle movement with water flow, but the particles are massless. So no, Washington Maritime modeling will not include debris tracking in the first pilot study phase, but we hope to add more modeling capabilities in the future. Carrie, I'm going to unmute you, so if you want to follow up with comments. I'm going to attempt to unmute you. Okay, Carrie, there we go. So Carrie, did you want to comment on that? Okay, well, maybe we can get them in to do a webinar in the future to talk about what the work they're doing up in Washington, because it sounds really intriguing. So we have one last question. No, sorry, Carrie, I can't hear you. But we'll chat offline and we'll see if we can get your information out to this group. Yes. So we have another question. Can we get this presentation in a PDF?
Yes, Althea, I can leave it with you, and then if you can distribute it from there, that would be great.
Yeah, I've been putting the presentations on the Google Drive so that they are downloadable along with any other information that you might want to share with that. So if there are no further questions, Dan, thank you very much for your time and willingness to reschedule after our technical difficulties last time. So we will be continuing this series of webinars over the next couple of years and longer if there continues to be interest. So we're interested in hearing your suggestions for topics. So please send me any recommendations for speakers or topics or improvements on how we can move forward. So our next webinar will probably be in June or July, just because of scheduling on my end. So send me those topics and let's get something scheduled so that it'll be on your calendar. This webinar will be available on the OEM YouTube channel next week, along with the PDF and other information as it comes out. So thank you very much for your attendance. Keep a look in your email for more information on future webinars. Thank you and have a lovely afternoon.